All right, let's jump right into it. Here's your rapid-fire explainer on semiconductor electronics. So, why care? Well, 3 direct questions came straight from this exact chapter on the 2024 exam. It all starts with energy gaps. Conductors overlap, insulators totally block, and semiconductors sit perfectly in between. At absolute zero, pure semiconductors are basically useless insulators. But crank up the heat, boom, electrons break free. Think of it like a job vacancy. When an electron jumps ship, it leaves a positively charged hole behind. To actually make these useful, we use doping. We purposely mix in impurities to massively boost conductivity. You've got 2 flavors. N-type brings extra electrons to the party, while P-type brings extra holes. Smash them together into a p-n junction, and a neutralizing 1 micron thick depletion layer automatically forms. Biasing controls the flow. Forward bias shrinks that barrier, letting current through. Reverse bias completely blocks it. Tweak those setups, and diodes become super practical tools, like voltage regulators, light detectors, or glowing LEDs. But there's a catch. LEDs need a minimum band gap of 1.8 electron volts to emit visible light. To shape power, full-wave rectifiers turn AC into ripple DC, and a parallel capacitor filters it perfectly smooth. Okay, let's talk logic gates. This high-yield topic practically guarantees 1 or 2 exam questions every single year. The rules are simple, really. An OR gate outputs a 1 if literally any input is a 1. Now, the AND gate is like basic multiplication. It only outputs a 1 if both inputs are 1. The NOT gate, incredibly simple. It just entirely flips your input. 0 becomes 1 and vice versa. Combine those and you get universal gates like NAND and NOR. They can build absolutely any logic circuit. So, what's the ultimate shortcut for simplifying these crazy complex circuits? It's De Morgan's law. Just remember, break the roof, change the sign. A plus becomes a dot, and a dot becomes a plus. Mastering this unlocks modern electronics. But honestly, how far can we shrink semiconductors before physics just completely breaks down?